3, 2, 1, let's go. So we're going to continue talking about how to solve non-homogeneous equations. Okay. So we know how to solve differential equations. So click this: second order linear constant coefficient. Specifically, find the general solution y sub h for the associated homogeneous version of the equation. So replace the f of t with a 0. Get the auxiliary equation, find the roots, plug it in, walk away. And we can find particular solutions now by making a pretty reasonable guess for what it should look like based on what f of t is, on method of undetermined coefficients, and there you go. Okay. But as we discussed and saw, the method of undetermined coefficients is not a robust method. It's a, well, let's guess something and see if it works. And if it doesn't, modify it until it does. Okay. Now, the only reason that technique worked was the right-hand sides we were looking at, their derivatives are nice, right? A polynomial's derivative remains a polynomial. A derivative of an exponential is still an exponential. Derivative of sine and cosine is still sine and cosine. So if the right-hand side was, oh, I don't know, secant, whose derivative is secant times tangent, trying to guess what's going to work is probably no longer an option. So what do we do? In fact, if here's a challenge for you. Pause the video and see if you can guess what the answer is going to. Try to undetermined coefficients this. Unless you've taken this course before, or you're like the greatest differential equations master of all time, you're not going to guess what the answer is. Trust me. But hey, if you want a good challenge, give it a go. Okay. Alright, so what are we going to do then? Alright, well, obviously we need a technique that works all the time, not just a, well, for this particular one, I've got a pretty good idea what to guess, let me guess it and work it out. We need something that's going to work all the time, right? We need a turn the crank method. We need an algorithm. Okay. So who's got the idea? Who's the smooth brain? So for this particular one, Joseph Lagrange shows up, and he's got a pretty good idea. Okay, so here's his idea. So look at y sub h. Y sub h is a linear combination of two functions, y sub 1 and y sub 2, where c1 and c2 are constants, y1 and y2 are linearly independent. Okay. Now something that we've seen before is, hey, let me take that constant and turn it into a function. Right, we've seen this idea kind of pop in where it's like, well, you know, if it's a scalar multiple, it's not. We know it's not going to work, so multiply it by a function and go from there. So, not the most ridiculous idea to say, oh, we've got some parameters here. How about we let them vary? Variation of parameters. Words mean things. All right, nice. Okay, so that's the idea. That's the plan. With one extra thing that's not immediately obvious. So Lagrange has this idea, but he notes that we're actually going to need something else in order to actually make this work. Not only do we guess that v sub p satisfy v sub p is of the form v1 y1 plus v2 y2, it turns out that we're going to want v1 prime times y1 plus v2 prime times y2 equaling 0. Now, for right now, this seems like just, okay, why? What? It's not obvious at all that you need to also throw this in until you actually plugged it in and tried it and saw that, oh wait, I need this, otherwise I'm in trouble. So this is, I'm using my mathematical clairvoyance to point out, oh yeah, we're going to need this. So keep that in mind. That will show up. Okay, so that's the idea. And again, we'll see why in a bit, why we're going to need this v1 prime times y1 plus v2 prime times y2 equals 0 bit. But let's go back to this is a fun differential. This is a classic one. Everybody has to suffer through y double prime plus y equals secant. This is the go-to one. This is like the default one. So the associated homogeneous is nice. It's y double prime plus y equals 0. That one you should just have burned into your brain somewhere. Like you're gonna solve that one so many times in your life. So just have it at the ready. The general solution for that is C1 cosine plus C2 sine. Okay. So Lagrange says that, all right, replace the C1 and the C2 with functions V1 and V2. Plug that back in and figure out what V1 and V2 need to be. Okay. Okay, so we need to take two derivatives. So let's take one derivative first. And, well, the product rule says the things get spicy. Okay. Now, note that if I were to take another derivative of this, before we even get into anything, another derivative is going to make this thing sprawl out massively, like to the point of like no return, basically, where there's just too much going on. And that's not a viable method, you know. Now remember, Lagrange also said something else. Not only is y sub p going to be a function times y1 plus a function times y2, the derivatives of these mystery functions have to satisfy this, right? My y1 is cosine, and my y2 is sine. So Lagrange says we also need this to fly. And now we see why, because the first derivative no longer involves the derivatives of v1 and v2. It only involves v1 and v2, right? And so, right, he says we need to include this, and like I said, at first it's like, why do you need that? Well, right now we see a very good reason. It makes the first derivative not a nightmare, which is nice. But we're also going to see something else. So let's take a second derivative. Very similar to the first derivative, because it's a very similar form. We get this. Now, when I plug this in, some magic happens. The second derivative, plus the original guess, oh hey, cancels. Cancels! Ooh, looky here. Let's regroup everything that we got now. So, Lagrange's slick move of requiring this equaling 0 turns my problem now into a system of two equations with two unknowns. Boom, right? So I now have two equations with two unknowns involving the derivatives, v1 prime and v2 prime. And conveniently, this is going to clean up super beautifully, right? Because let me go ahead and multiply the top by cosine and the bottom by minus sine. Well, now when I add the two equations, well, cosine squared plus sine squared is 1, so I just get v1 prime is negative tangent, which integrates nicely to log of cosine. Now note, again, this is one of those cases where we do the thing that we always wanted to do in calculus, and that's forget the plus c, because by context, we don't need every possible antiderivative, we just need one explicit antiderivative. If you want to be goofy and do like a plus pi or something, go ahead. You're still going to get the right answer, but it's going to look dumb. Alright. So, we figured out v1 by cleverly multiplying and adding. If you do a different multiplication and adding, so note that I did choose cosine and sine to delete the v2 prime term, the v2 prime term, so I could solve for v1 prime. If I do a similar thing to eliminate v1, well, then I get v2 prime is 1, so v2 is x, and I now have my particular solution. v1 I know is log of cosine, v2 is x, and so hey, there's the particular solution. It's log of cosine times cosine plus x times sine of x. So like I said, you had no way of guessing that this is what the form needed to be. Right? There is no way you could have possibly guessed. And note, secant doesn't even show up here. Right? There's like the right-hand side was secant, but the answer, no secants. No secant. You're the secant. Okay, so that means we've got the general solution now. Take the homogeneous, add the particular. The homogeneous is C1 cosine plus C2 sine. And we got the particular solution using Lagrange's method. Boom. There we go. That's it. Alright. So, there's probably a quicker way to do this. Yeah. Now, the method I just showed you, you're free to always use it exactly like that. If you liked everything I just did and thought it was the coolest thing ever, go ahead and do it. But obviously, Lagrange figured out some explicit formulas to help us out. So there are actual formulas. So, and your textbook goes through the derivation, so go ahead and check that out if you're interested. But basically, if you're looking at a linear, second-order differential equation, note, not necessarily constant coefficient. Right? You get a variable coefficients, turns out. This method is pretty cool. Okay, so if I give you this, and I've told you what the general solution is to the associated homogeneous, then the particular solution, let the parameters vary, C1 to V1, C2 to V2, then there are always explicit formulas we can use to solve for V1 and V2, and here they are. Right? So you may have noticed that I technically was using these sorts of things. If you had a keen eye, you might have seen some things that are like, wait a minute, I know what's going on there. And if you've got a keen eye, maybe you notice something else. That division is totally fine, because I know the Wronskian, which is what the denominator is non-zero, so I'm never dividing by 0. Nice! It's good stuff, man. It's pretty slick. So, yeah, so it turns out that the formulas will always pop out this way. You don't need to go through the whole rigmarole that I did. Feel free to do it, but here's a quick shortcut to get right to the answer. So that being said, now that we have these shiny new equations, let's give them a go. Time for another one. And that is sine of e to the x right there on the right-hand side. So now that we got some beautiful new formulas, go ahead and pause the video, give it a go. Take the Dr. Pepper break. Hear all these gross sounds of me eating and drinking. Alright, so let's go. Alright, so again, first thing you should always do, we're trying to solve non-homogeneous second-order linear constant coefficient differential equation. Always need to solve the associated homogeneous. So set the right-hand side equal to 0, get the auxiliary equation, get the roots, c1 e to the negative 2x, c2 e to the negative x. Alright. So now we want to get a particular solution, and as we can see, the right-hand side is significantly aggressive, right? Sine of e to the x. Probably no way to guess what the right format for what it needs to be, right? If you take the derivative of sine e to the x, right, you get e to the x, negative e to the x, e to the x cosine e to the x. So trying to guess a form is probably not an option for us. So that's why Lagrange comes in and helps us and says that the particular solution, let the parameters vary, replace the C1 and the C2 with V1 and V2, and we've got formulas for what V1 and V2 need to be. Okay. So before we go all into it, I always recommend doing the following. As we saw, the Wronskian shows up in the denominator of these formulas, so let's go ahead and compute that. So here we go, the y1 times the derivative of y2 minus the derivative of y1 times y2. In this case, it ends up being equal to e to the negative 3x. Alright, so we know then that v1 prime will be negative y2 times f of x, all divided by the Wronskian. The Wronskian we just computed. F of x, again, remember, is the right-hand side. And I want to point out back here again, we want to make sure the leading coefficient is 1. Because as the formulas dictate, we need that. If there's something attached to y2, you need to divide out by it first. Alright, that being said, we know the right-hand side is sine of e to the x. We have our y2, e to the negative x. That cleans up the negative e to the 2x, sine of e to the x. And now, you're looking at this, and you might be having the heart palpitations. You might be getting a little sweaty. And you're looking at it going, oh no, I need to do an integral. I got to integrate negative e to the 2x sine of e to the x. How the hell am I going to do that? Well, I kind of spilled the beans a little bit earlier. We know the derivative of sine of e to the x is e to the x cosine times e to the x, which is the chain rule. So the integrals aren't going to be that bad, right? And here I worked out the details for you. So negative e to the 2x sine of e to the x dx, well, you've got a function buried inside of another one, so the first thing you should try is a u substitution. If you let u equal e to the x, okay, well then du is e to the x dx. So we'll have sine of u. We have e to the 2x, which is e to the x times e to the x. So one of the e to the x's gets removed from the du, and the other one is just u. So it's the integral of negative u sine of u du. I spared the details on that, but then that's just an integration by parts. That turns out to be this. And again, note, no plus c, because again, I don't need the plus c. Well, I just need any derivative that will work. So we get there. All right, and I started with x's. I currently have u's, so make sure we do the back substitution. Replace the u's with e to the x's, and hey, there we go. The integral of negative e to the 2x sine of e to the x, not too bad. E to the x cosine e to the x minus sine of e to the x. That's the most ridiculous thing. All right, so we solved for v1. All we got to do is solve for v2, and then we're home free. Okay, so what's v2 prime? It's y1 times the right-hand side, all divided by the Wronskian. And this one actually ends up being a little bit easier to handle, because it's just e to the x sine of e to the x. So the integration here, and ooh, I'm a bad boy and done on my dx. Let me fix that. Almost made it. Got to the last slide before I caught a typo. Don't tell me there was a typo before this. There wasn't. Alright, so this one integrates out. Nice. And simply, we get negative cosine e to the x. Alright, so now I have v1 and I have v2, so let's plug it all in, and in fact, it cleans up quite nicely, and we get something, negative e to the negative 2x sine of e to the x. It almost feels like you could have guessed that, right? That's pretty close. Like, maybe if you stared at it long enough, you would have figured it out. But variation of parameters here, of course, is a very robust technique. It's just a formula, so it's turn the crank a lot better than variation of parameters. But no, this is a lot better than undetermined coefficients. Right. Although we see there is a bit of a trade-off, whereas undetermined coefficients is kind of just plug in and solve for constants. Variation of parameters, sort of like finally, in the second order case here, you actually have to do some, not impossible integrals, but some more sophisticated ones. So here we see actually solving a DE requiring us to use the inversion of derivatives integration. But anyway, so we've got the particular solution, so now I can combine the homogeneous and the particular to get you the general solution. There it is. It's a good time. All right. So that is pretty much the story for constant coefficient second order linear differential equations. Now of all the techniques we know we'll need to solve them, so it's probably a good time to look at an application of this stuff, and that's what we'll do next time.